And next up, we are staying on the theme of data and data management, but we're moving from the simulated to the real life data and what is, I think, a very common problem for most people involved in anything to do with humans, which is missing data. And here we've got Denver Brown from the University of Texas at San Antonio, who, if I'm right, Denver primarily works in sport and health psychology. He's going to talk about best practices for handling missing data. Thank you very much, Denver.
Awesome. Thanks for the intro, Emir. And first, I will preface this talk by saying that I am by no means an expert in handling missing data, but I have learned a few valuable lessons over the past couple of years as I started to delve into some of these better practices. And I've learned quite a bit in being part of a manuscript that I'll touch on in just a second that kind of formed the foundation for this talk. So the foundation for this paper, Best Practices for Addressing Missing Data Through Multiple Imputation, was created during a hackathon session at SIPS, which is the Society for Improvement in Psychological Sciences, kind of what we have here at STORK are creating our version within kinesiology. So this paper is something that was a hackathon there that they invited people to be a part of and learn about best practices for handling missing data. It ended up turning into this current preprint that's under review. So I tip my hat to Dr. Adrian Woods, who's led this project. I've played a very small role in it, but I really want to talk to everyone today about this paper and some of the implications for kinesiology research. So if you're interested in learning more about this paper, the preprint is available at this QR code. There's actually a decision tree that you can follow through, and I'll show you some of the slides near the end of this talk, as well as a decision tree infographic on what you should do going from you have your data, now what's next, all the way to analysis. So it provides a really good flow of those steps that you want to take along the line. So why is this relevant to the mission of STORK? And I really think that if we want to truly prioritize improving our methods and practices within our respective disciplines, then we need to learn and implement appropriate and replicable methods for adjusting for missing data. And I truly think that handling missing data is part of this methodological reform that we need to follow and really push kinesiology forward so that we can make more accurate and more and stronger claims. You also see an example that I'll provide a little later in this talk that handling missing data is really important for diversity, equity, inclusion, and accessibility improvement efforts, because we know and many studies have shown that certain people are less likely to respond to items on questionnaires. Think about someone who might have a disability. They might not respond to a question about how physically active they are. That's just one example, but you'll kind of see as I go through this talk. So as Emir kind of stole my punchline right before beginning this talk, incomplete or missing data is a common challenge in kinesiology research, whether you're in exercise psychology, epidemiology, biomechanics, physiology, you're going to deal with these challenges. And we can have these challenges from participants failing to complete tasks or questionnaires. This could be that they don't complete parts of a questionnaire. Maybe it's some of the items that they don't do, or maybe they even stop responding during a task measure. It could be during a Stroop task. They just quit pressing the button that they need to respond. We also have missing measurement occasions. So there's in kinesiology, we have plenty of longitudinal studies or randomized controlled trials that have multiple visits, and sometimes people just don't show up, or even worse, we can have people who just completely withdraw from our study. And these are three of the main sources of missingness that we can experience. But the reason why I'm giving this talk is because I think that handling missingness is far too often overlooked. And I will say that, coming from my graduate training where I studied at McMaster University, which is thought to be a really good kinesiology program, and I truly believe it is, I didn't have any formal training in handling missing data. You kind of learn things through people in the lab, but in kinesiology, I think we have a lot less courses that are tailored to things like handling missing data than in some other disciplines. So I think we're a little behind the curve, but hopefully this will provide us with a bit of motivation and impetus to see the importance of how we handle missingness within our studies. So the first thing I want to talk about is the types of missingness that we experience. So you might see this at the top, MCAR, which refers to missing completely at random. And you might think, I've run Little's MCAR test to determine if my data is missing completely at random. And so what this is missing data are the result of a truly random process. So the likelihood of missing the likelihood of having missingness is the same across all our data points. And missingness is unrelated to other measured or unmeasured variables. However, I will point out that it is extremely rare to have missing completely at random missingness if you don't have a planned missingness design. Now, you might run Little's MCAR test and see that you have missing completely at random data, but if you have a more complex data set with, let's say, 5 to 10 variables or even more, you're probably going to see that your data is not missing completely at random. Now, the one way that we can have missing completely at random is something called a planned missingness design, which I don't think I've seen much of within kinesiology research, but I'll give you a couple examples of what could happen. So in one such design, each participant is only given a random subset of the assessments to complete. So everyone is getting different things. In another type of planned missingness, a random subset of participants is given more expensive and valid measures above and beyond inexpensive designs. So that could be, maybe you have a large study that's looking at physical activity behavior over time, and you're going to use something like the IPAC to measure physical activity, a good validated self-reported measure. But among this, you want a subsample that's going to be going to have movement measured using accelerometry, and we know accelerometry is expensive and resource intensive. So that might be one way in which you would do this. And then lastly, in a third variation of the planned missingness design, participants are given random subsets of scale items in order to effectively collect data on more variables while minimizing the burden on any given participant. So when we have missing completely at random, it's considered completely safe to ignore our missingness and just do a complete case analysis. But there are some limitations to this still. We can our precision of our estimates will be reduced because we would be reducing our sample size. We know that when we get bigger samples, we generally have more precision. And unfortunately, it really is impossible to know whether data are missing completely at random unless it is designed by the researcher. Now, you're probably wondering, well, how do we handle this then? What's probably most likely is you have missing at random. And this is a systematic pattern of missingness that can be accounted for using information contained within the data set. So you're going to have between group differences for rates of missingness. So an example of this would be students who are less physically active at baseline in a longitudinal study are less likely to participate in subsequent waves. So you'll have missingness on physical activity in those subsequent waves. And we can predict this, or we know this, that missingness is dependent on baseline physical activity levels. So we have variables within our data set that provide information that could help us model what's going on here. So lastly, we have missing not at random. This is kind of the worst thing that we can possibly have. And this is where you cannot fully account for missingness through your measured data. So the previous example I provided, we had physical activity at baseline was something that we could predict missingness from. In this, we have no variable that can predict missingness. We can really only theorize about why this occurs, which is pretty problematic. So a quick example of this, and this isn't specific to kinesiology, the best practices paper that I was working on is specific to developmental psychology. So some of the examples I'll provide are related to that field of inquiry. So here we could say the example is that parents of children experiencing more behavioral concerns may be less likely to return questionnaires on the impact of certain parenting practices on that child's behavior. But we have missing values for behavioral, the missing values for behavioral problems really depends on the missing behavior score. So we don't know that about them. We can theorize that that's the reason, but if we haven't measured that variable, then we can't really say and include this in our modeling techniques to handle missingness. Now, how can we handle missingness? I know we can take two different routes, and a lot of times it is very attractive to take the easy route and just go directly from A to B. And oftentimes, I would say the easy route would be doing things like list-wise deletion or complete case analysis, or pairwise deletion, where you have complete data for the variables of interest that are going to go into your given analysis. Now, both of these techniques are easy to implement, and I'll say, sadly, they are still readily accepted by many in the field. I've seen plenty of papers that have come out within the last 2 years that just say, we performed a complete case analysis. Missingness was not accounted for whatsoever. And this is really problematic. I was going through Sammy Chekroud's 2018 Lancet Psychiatry paper looking at the relationship between exercise and mental health just earlier this week. And this was a really good paper. They used some pretty advanced techniques. They used generalized additive models or splines to model nonlinear relationships. They use covariate balancing propensity scores to handle the differences that may exist between participants. But then when I got to how they handled their data, they only did a complete case analysis. So they have two really forward or thought forward approaches. And then for missingness, it was just complete case analysis. So even with really strong papers that come out of great research teams, we're still seeing the easy route being taken in handling missingness. And both listwise and pairwise deletion are really problematic. They reduce our statistical power because it depends on your sample, but you could lose, depending on what variables you have in there, 50% of your data, going from 1,000 participants down to 500, which is problematic and can further increase bias in our data because of who is being eliminated. Maybe it's people of a certain race or ethnicity, or certain age, or their disability or chronic health condition status. Losing these individuals from our analyses is really going to bias our findings, which creates some downstream problem, which I'll touch on in a second. Due to losing all these cases within our analysis, we also create inefficient estimation of our parameters, our confidence intervals, and our significance tests. We might have less precise estimates, but our estimates might also be off by, I don't know the exact effect size, but in the example that I'll provide later, you'll see how dramatic that this can be. And they also create constraints on generalizability. So because what we find is biased, we're kind of limited in what we can say about it, but a lot of people still carry forward and give the implications or what should be done and how generalizable it is, even though they just got rid of whatever percent of their data that was available. So why is deletion bad? And I'm not sitting on a pedestal here saying I've never done this and poo-pooing on everyone else. I have done these techniques, pairwise, listwise deletion. But now that I've learned a bit more about how to handle these properly, I want other people to know this too. And the one thing I'll say, and I'm sure all of us here at STORK within this community know, that science isn't meant to be fast. It's a slow process that takes a lot of careful insight to have as strong of claims and as accurate of claims that we can, so that we can actually make a difference in the research that we're doing. So why is deletion bad? As I said earlier, some participants are more likely to have missing data than others. At the same time, these biased results can therefore influence the interpretation. Maybe we're saying that this is a stronger effect. Maybe we're saying it's a weaker effect. That can be important depending on what field you're in. And then at the same time, we have work that's going to follow on this, because you think of the slogan on Google Scholar, standing on the shoulders of giants. We're always building on research to move on and progress and open new doors. So the preceding work after this biased research has been released is also going to be biased, and we will have problems with replicating this work. This is problematic, and this is something that we here at STORK are trying to create this methodological reform to reduce these issues. Now, what's the worst case scenario? I just kind of want to paint a bleak picture. Well, there could be interventions or policy recommendations that are implemented that are grounded in biased results due to an entire biased line of inquiry. So this is the worst case scenario, but something that could happen. You think of all, you listen to James Heather's talk and hear about all the COVID research that went on, some that proved to be well done and rigorous and others that weren't, but some of it still gets pulled into our systematic reviews, and it can actually influence some of these decisions that are made by policymakers. So this brings me to the point of this talk. Is there a solution? Yes, there are best practices for handling missing data. So there are certain techniques that can approximate what the results would look like if we had complete observations. So we can use things like full information maximum likelihood, which is common in structural equation modeling, which might be more common for people that might be working in things like psychology. But I'm not going to talk about that. I'm going to talk about multiple imputation today. So multiple imputation does not completely fix the problem. There is no complete fix to any of these problems because the data is still missing. We need to figure out what we can do with it, but we can help reduce the bias across several different scenarios, whether we have missingness on 2 variables, 10 variables, 50 variables. We can have some workarounds here that can reduce bias, and multiple imputation is considered a feasible, credible, and powerful approach to handling missing data. We can retain everything we have here. So you're probably wondering, what the heck is multiple imputation? And I'll kind of walk you through how it works. So what multiple imputation is doing is using existing data to generate multiple data sets of plausible values for missing data. So when we say multiple, that refers to having more than one data set that's created so that we can have some randomness that's built into what we see. So as I said, these random components are incorporated into each data set to reflect the uncertainty of these values. So we don't know if our participant 1 reported a 4 on this value, if they reported a 2 or a 5, but we can use other variables that are related to our variables of interest. So say we're looking at the relationship between physical activity and mental health. Well, we're going to have auxiliary variables that are in, or we're going to have other covariates that are included in here. We're going to have other auxiliary variables that we know are related to not only our independent variable, but also our dependent variable. We're going to use all this information to predict, based on all the information that's available within our data set, what these values could look like. Now, we don't want to do it with just single imputation, which sometimes you might actually need to use. I know with some R packages, you can't load multiple imputation, multiply imputed data sets into there. So sometimes you might need to use a single imputed data set. But for the most part, we want to use more than one. And there's the rule of thumb that a lot of people talk about using 5, but you want to use, it's often recommended that you refer to the fraction of missing information, which could be, let's say, 9.3% on physical activity. And you generally want to have more than 9 multiply imputed data sets for this. And there's a good paper by White and colleagues in 2011 that discusses this approach. So what would it look like in our 5 multiply imputed data sets? So for one value, you could have a missing value that could be 4 in 3 of the data sets. It could be 2 in one of the data sets, and then 5 in another. So not every value is going to be the same, and that reflects that random component that's brought into the analysis. Now, then what we're going to do is we're going to analyze each data set individually according to our common statistical model. So this could be running a logistic regression model, linear regression, analysis of variance. No matter what it is, you're going to run them all singularly. And if you're doing this in R, there's some great ways that makes it really simple on you to do this. And then lastly, according to Rubin's rules, we're going to pool everything together so that we can have one set of estimates, variances, and confidence intervals. And that's it. That's multiple imputation in a nutshell. There's obviously a lot more to it, but essentially you're creating multiple data sets with randomness incorporated into it. Then you're going to analyze all these data sets individually and then pool them together to look at the estimates. So one thing I will highlight, getting back to our types of missingness, is that most modern methods of handling missing data assume missing completely at random or missing at random. And when data is missing at random, variables that account for missingness should be included into that imputation model. So if you're using the mice package in R, You're going to include variables that predict your independent variable as well as your dependent variable. And these do not only need to be the covariates that are going to be included in your, let's say, logistic regression model. These can also be auxiliary variables that are related to your independent dependent variable, but ones that you're not going to include in your regression model. And these can help strengthen the accuracy of your multiply imputed data sets because you're using more information that's available within our data set to make better estimations of what each data point should or could be. Now, if we have missing not at random, at this point, there really isn't a consensus about handling this type of data. The bias within missing not at random really cannot be resolved. But it is argued that multiple imputation is a better solution than ignoring missingness. And this is particularly when we've included these auxiliary variables to add additional information into our model to better predict what these values could be. So how are we doing in kinesiology? Unfortunately, multiple imputation hasn't been widely adopted. I've been able to find one paper that looked at missing data reporting and analysis that was done in motor learning and development. If you look at the abstract here, I highlighted some key takeaways. You can see that it says researchers predominantly used older methods, mainly deletion, for analysis, which only showed a smaller increase in the use of newer methods in 2017. And they go on to really point out that improvements in missing data handling may have the merit to address some of the major issues, such as underpowered studies in motor learning and development. And, some of the previous speakers so far at this conference have already talked about how we have small sample sizes in certain areas of kinesiology research. And having one or even two participants drop out or miss one session and losing their data, this can have a major impact. That could be 10 to 20% of your participants. So having some ways that we can handle this, and the best practices for handling this to improve our sample size and our power by retaining participants or estimating their data is really important. Now, why do people not use multiple imputation? There's many reasons that have been cited in the literature so far. Now, it could be due to a lack of transparent and reproducible guidelines. So there isn't a good knowledge on streamlining the process by which missingness can and should be handled. And hopefully the paper that Adrian led is something that people in kinesiology can go to now, because a lot of things that are done in developmental psychology have some relevance to kinesiology. I think it's a key tool that I really encourage you to go look at and read and learn a bit about it, and use all the supplementary materials that are available there. There's plenty of code that's available for different statistical programs. Another one is a lack of familiarity or confidence using statistical software. This is something that people can learn, and hopefully I'm providing you with some familiarity about what multiple imputation is, and you have the time that you can go view how this can be implemented. At the same time, we know that there's also some disparities in terms of training opportunities, resources, or mentoring that people might encounter. And what might be more problematic is that there is pressure from colleagues or advisors to follow the already established norms, things like listwise or pairwise deletion, to facilitate quicker turnaround on publication of manuscripts, which is really problematic and is already being highlighted by several people today about how we need to get away from these questionable research practices. At the same time, point number 5, there are worries over whether the decisions implemented are correct. And lastly, it is added complexity in the data analysis process. But again, I think it's something that we really need to focus on, because science doesn't need to move at a rapid pace. We need to take time to do things right so that we can have less biased estimates and information that's going to be used for decisions down the line. Also talk quickly about some misconceptions about multiple imputation. So I'll go through 5 that were in this preprint. So the first one is that only use multiple imputation when too few cases are left after listwise deletion. And the reality is that multiple imputation has advantages even when the amount of missing data is low. So even if you only have 5% missing data and you have a 5,000 participant sample, you should still use multiple imputation because it can increase the precision of your estimates and reduce your bias further. Certain variables must not be imputed, whether it's outcomes or predictors. With the exception of special instances, most variables can be multiply imputed with several benefits to be reaped from it. So I've encountered people who have said you never want to impute sex or gender or race or ethnicity. There are certain instances where you might not want to, but for the most part, these could be predictors of missingness, and we therefore want to impute these and try and include more individuals within the sample and use as much information as we can to try and determine what their assigned value would be so that we can make better inferences for that specific category. Now, the third one I point out here is something, my wife's an accountant, and she kind of laughed when I talked to her about this paper and this talk I was giving, because in accounting, it would be fraud if you made up data. And she said, oh, how can you do that? How can you just make up data to go into your analysis? But again, this is an algorithm that's using all the available data to try and optimize the accuracy of the missing values that are being replaced. This isn't just Diedrich Staples sitting in a park and just kind of fraudulently making up numbers that he wants to put down on a paper. This is something that we're using an algorithm that is looking across all the data to try and be as accurate as possible. Also, doing anything other than listwise or pairwise deletions is hard enough and not worth doing. Well, hopefully you see with this and some training that we can develop the skills to handle missingness using multiple imputation. And this can be computed or completed in a reasonable amount of time. Like this is something that you go on YouTube these days and you can find so many different videos and so much content that can walk us through this and really streamline the process. You don't need to go and read a paper, even though I would encourage you to read Adrian's preprint, but you can go and watch a video if you'd rather see that and see the code right there. And lastly, the computational demands of multiple imputation are too intensive or it would take too long to compute. So we have Murphy's Law and computers are getting more powerful by the day. So there's only in rare cases where you're using complex analysis or big data or something like MRI data or maybe genomics research that you're going to have computational constraints. So we're probably going to be okay in kinesiology for the most part to use something like multiple imputation. Maybe it needs an entire night to run, but you should be able to come back in the morning and you have your multiply imputed data sets there waiting for you. All right, so I talked about giving you an example of the disparities that can occur if we just use something like listwise deletion. So I'll walk you through this example of how missingness can influence our findings using data from Jason Nissen and Ben Van Duzen. So this is looking at assessment prior to and following an intervention to improve student knowledge. So we could think of the same being in a resistance training study, as Dr. Swin was just talking about, James was talking about earlier. And again, we know already from previous data that students achieving lower grades are less likely to complete a post-test. So how can we handle this so that our post-test results aren't skewed or biased? Now, what I'll show you here is the collected data, and this is listwise deletion showing the difference between students who are thought of as advantaged versus students who are thought of as minoritized in terms of their test scores. So without multiple imputation, you can see that the advantaged students were scoring roughly 68% on the test, whereas the minoritized individuals were scoring 63%. So we can see that there's a Cohen's d effect size that's in the small to medium size range at 0.43. Now, listwise deletion of these data would lead to more students who earn C's and below being removed from the data set, which would bias findings to reflect the outcomes of top performing students. So this actually hides much of the impact of the structural barriers to success for minoritized students by disproportionately removing data from these minoritized students. So when we use something like multiple imputation, when we use multiple imputation to look at the true data, here you can see that the advantaged students actually score 65%, so a little bit lower than what we're seeing in the listwise deletion example, whereas the minoritized students are actually scoring 10% lower, all the way down to 53%. And when we look at this effect size again with multiple imputation, it's a large effect size now, or medium to large effect size of D equals 0.75. So here you can really see how using complete case analyses can skew our findings about inequities across student groups. Now, if you're interested in physical activity epidemiology, this might be another area where this is really applicable. Or perhaps when you're looking at exercise training studies and you're looking at things like maybe differences in hormones, how they drive these changes. So I really want to highlight here how this can occur and show you the disparity in effect sizes that we'll observe when we do not use the best practices versus when we do. So in the last 10 minutes, I'm going to walk you through a brief overview of the procedures to implement multiple imputation. So this is really the decision tree that Adrian put together, and I'm showing you the infographics that that were put together and are available on Miro for anyone to view. So the first step in the decision tree is theorizing about potential missingness. So you want to think about, could your data be missing completely at random? Did you have a planned missingness design? Or is your data missing at random? Can you predict what's going on in terms of why you have missingness on your independent and dependent variables? And then lastly, non-ignorable missingness. Could your data be missing not at random? So you want to think about what variables might be related to missingness in your data set, because you want to be including these into your multiple imputation model. So the second step is to decide which method to use. So for sake of this example, let's just say you're going to decide to use multiple imputation. If you are using structural equation modeling, you might just want to use full information maximum likelihood. But let's just say that we're going to use multiple imputation here. So you could go through and use deletion methods such as listwise or pairwise if you have missing completely at random. But if you have missing completely at random or not at random or at random, you'd be better off to use multiple imputation for the variety of reasons that I already showcased earlier in this talk. So now you've picked your poison and you've decided that you're going to use multiple imputation. What are you going to do next? So a good thing that is optional but strongly recommended, we're talking quite a bit about pre-registration here at the STORK conference or the STORK summit, is to pre-register your missing data plan. So you want to pre-register the variables that are going to go into your missing data analysis. So that could be not only your covariates that are going to be included, but also those auxiliary variables that are also going to go in to hopefully optimize that algorithm and increase the odds of having more accurate predictions. So in terms of decision tree step 3, this is where you first want to start testing for your missingness mechanism. So you want to examine your patterns of missingness. It could be on entire scales, on items within scales. You want to look at patterns of missing data points, because maybe you had an error within your Qualtrics survey and one scale actually didn't get administered. That could be something that you need to look at and determine whether it was a reason why you had missing data. And then you want to look across groups of people as well as in univariate and multivariate descriptions. So you want to be able to evaluate the amount of missingness on each variable of interest. So primarily, I'd say focusing on your independent variable of interest as well as, or independent variables of interest and your dependent variables of interest. Now, you want to move on and then choose a decision rule for determining whether missingness is related to other variables in your data set. So what you're going to do is use certain statistical techniques to look at these relationships. So it could be chi-squared tests, it could be correlation, it could be regression or ANOVA, to try and figure out what predicts missingness. And that's a key step and something that's actually not too challenging to do. If you take a basic statistics course, you're going to learn about chi-squared tests. You're going to learn about correlation. So these aren't things that are far removed from our toolbox that we've already developed through our graduate training. And then we want to look and check whether any auxiliary variables are related to our missingness. As I've said before, if we can include these variables, we can help to optimize that algorithm. All right, now getting on to data carpentry. So pulling out more tools in your tool belt. You want to do the typical things that you would do in your analysis, checking for normality, transforming variables if you must. And then we want to go on and impute our variables. So what are we going to be imputing? Dependent variables. Maybe we only have missingness on one of our independent variables, and we have full or complete data for our dependent. So we want to look at these things, and we want to set up our data set. If you have weights that would be included, these are things that can go into your imputation model as well. You also want to see whether it's a multi-level model. Do you have students nested within schools? Do you have schools nested within school boards? And you have plenty of that. So if you're looking at something like the YRBSS, the Youth Behavioral Risk Surveillance System in the US, you're going to have nesting here that you're going to need to account for. Students within schools, within states, across the US. So these are things that you want to consider when you're putting into your multiple imputation model. All right, I know this one's a little challenging to see, but this is where, I encourage you to go into the Miro board and look at this infographic a little closer. Here's where you want to choose your multiple imputation model. You've probably most often heard about MICE, which stands for multiple imputation by chained equations. That's the MICE package that was developed by Stephen Van Buren and colleagues. There are other options though, Markov chain Monte Carlo, or multivariate normal imputation. So I'd say that MICE is probably the most common, probably one that if you look at the supplementary materials from Adrian's preprint, one that you could probably easily run. Then you want to set up your imputation model. Again, try and make, well, don't try, make it reproducible. Make sure you set a seed number. I always go with my son's birthday when I'm setting my seed number, something that's memorable to you. It could be 1, 2, 3 if you want it to be. And then you want to go on and choose the number of imputations. So let's say you have a fraction of missing information of 9.3%, then maybe you want to do just above that and do 10%. And then you want to move on and check that your imputation model worked after it ran. So there are some excellent plots that are provided if you're doing this in R using the MICE package, that you can see that this is working. And generally what I like to do is also just subset my multiply imputed data sets to look at one data set and just make sure there's not any crazy values or something strange that happened within there. Now, lastly, this is getting into how we analyze the data. So you want to report your results for what you're seeing. Again, you want to tell people about the amounts and rates of missing data, including for your auxiliary variables. Talk about that missingness mechanism within your, could be in your data inspection portion of your results section. Depends on where you want to set it up. If you like to put it in your methods or your results, you want to report your multiple imputation model setup, and then look at the results from your checks and make sure the imputation worked. So once you have this, you can move on and run your analyses and pool everything together using Rubin's rules, and hopefully you've preserved your data set and you can make a less biased and more precise estimate that will help reduce bias that we see across the literature when we're using things like listwise or pairwise deletion. So I actually finished a couple minutes early, but everyone's probably happy. I'm sure we could all use a break at this point. But if you want to check out the preprint, again, here's the QR code, same for the decision tree and the decision tree infographic. I'm always happy to talk about these things. Again, I'm not an expert in this. I know a little bit, but hopefully we all have taken in some information that might be worthwhile and help improve our statistical analyses.
Awesome. Thank you so much, Denver. So much in there. Extremely useful information and great presentation. I think you're pretty much finishing bang on time. We have scheduled a short break now. Denver, there are a couple of questions and comments in the chat. Perhaps, obviously, take a break first, but perhaps if you have time to have a look at them, if you have any advice or thoughts, that would be great.
Yeah, for sure.
I won't suggest that we talk about them now because we only have a 25-minute break before we get into the next section, and we've had 3 super but intense talks, a lot of information to take in. Not 3, 6. There's been a lot going on. So I'm going to suggest that we take a short break now, and we're going to meet back here at what time? Again, depending on your time zone, 11:25, basically in 25 minutes. Go get something to eat, stretch the legs, do a few jumping jacks, get the brain moving. And if you fancy it, head into the general chat breakout rooms. And when we come back, we're going to have Paul Gorzinski and Jaffer Thomas speaking. Then I'm going to give a brief update on a STORK project that's ongoing. And we will finish then with Kristen Sainini, who will describe her wish list for statistics in sport and exercise science. So to everyone who's presented so far, thanks so much. I think it's been a great morning, so much to take in. And yeah, go take a break and we'll see you here in 25 minutes.
Have you been saying stop